Today we are going to do section 2.5. First, let me scan the book. Let me remember to hold it the right way. Okay, so here it is. Let me get it to be parallel. Yeah, that looks okay, I guess. A little closer. Oh, actually, this is just for this part, right? Because we already scanned it. So I'll put that a little closer, and that should do it. Okay, next. This is page 80 and 81, I think. Let's see. Let me line this thing up. This look lined up? I guess that looks okay. It looks kind of tilted. A little closer. Well, all right. And anyway, so this is focus a little bit on top and a little bit on the bottom. All right. Okay, next, this is page 82, 83, I think. Why is this thing all tilted? Maybe like this or something. Well, yeah. Anyway, all right, that should be close, good enough. Okay, and then a little bit closer on top. And a little bit closer on the bottom. All right. And finally, here's this one. Let's see. Okay, there's the last page. Is that close enough? That should be okay. All right. And then zoom in a little bit on top and a little bit on the bottom. Okay, so that should be it. So let's now do section 2.5. First, we are going to do something called the del operator. It is nothing new, okay? You've seen this before. The del operator is the partial derivatives. Let's look at the bottom of page 79. The partial derivatives to each component. So then, and it works like a vector, even though the del operator is not a vector, but it works more or less like one. And for example, let's turn to the next page and look at a del operator. What is del f? Del f is called the gradient. Okay, that is del of f of say if we have del f. F some function, right? A vector function. So del f is these three components. It is a vector. And it is, of course, called the gradient. Next, let's look at definition 3. What if you have some del f is added together? You add these three components together, and from calculus 3, you might or might not remember, doesn't make any difference. It's called the divergence, is you add all this stuff up. In other words, divergence y is also called del dot y because it ends up looking like the dot product of the operator dot the vector. Next, what if we have del cross y? And you might remember from calculus 3 or something, or 2 or 3, I don't know which. Anyway, del cross y is called the curl, okay? And you do it just like the cross product, actually. You do all these subtraction and everything will come out. And next, we will, this is something that you might not remember as well, but it was mentioned in calculus, in basic calculus. And this is the last called Laplace transform. Okay, you could call it the Laplacian, same thing. Which is del dot del f, which means we do the second derivative and add it all together. And then this equation has a name for it. It's called the Laplace differential equation. That's a second order equation, and the solution is called a harmonic function. You might have remembered that word from back the old days of basic calculus. So then now that all this we have already done, so please that you have learned in the past. So please be sure that you read it yourself carefully, okay, to refresh your memory. And then we have some basic examples here. So there's some function, and you might calculate the grad of, and also notice that del dot del. By the time you get through the partial derivatives, you realize and plugging in numbers, and you realize it happens to be 0, which means this is by definition a harmonic function. This thing. That is. well, anyway, so please work through that yourself. And similarly, for example, B, that thing we're calculating the divergence. Okay, go back up there and figure out what divergence is. If you've already forgotten, it's in definition 3. Follow the formula, and then also calculate the curl, which was del cross y. So after you work out some stuff and come up with some kind of a solution. So please do that yourself, so that we will, let's look at the next page, page 81, where we are considering the directional derivatives, which is the same thing as we learned in the previous chapter, okay, except that now it's in 3 dimensions. The directional derivatives is defined exactly as it was earlier, again, with a difference of being in 3D. So then the only difference then, of course, is that being in 3D, we have 3 variables that goes along, right? And so that you have the first one, the second one, the third one, but otherwise it looks identical to the 2D version that was mentioned in chapter 1. So then in the And of course, the directional derivatives also mean the same thing, although now that we have 3 independent variables, we can no longer graph this thing in the Desmos 3D calculator, because if you have 3 variables, we need a fourth dimension to graph it. And unfortunately, we humans live in the 3rd dimension, and it's not possible for us to visualize any 4th dimensional object directly. We can only but we can still investigate it. That is, we can figure out its properties and stuff like that, but we can no longer graph the thing. Well, we can graph its shadows. That is, we can graph part of it, like its projection, 3D, that sort of thing. But unfortunately, we can't graph anything more than 3D, okay, for real. So, well, at least I don't have a calculator that will do it for me. So then, but it's still okay. All right, so at this point in math, you start getting used to the fact that we can't always visualize what we're doing, but we can still do it, okay? Because we'll do it the same way as we did back in the 2D, when we could visualize this thing. So then we have the directional derivative. Of course, if you're taking along the direction of the major axis, it's just the partial derivatives, just like in 2 dimensions. And then as in the back in the day, which was on page 40, okay, the 2D directional derivative was defined on page 40. And also on page back in the day, there was some kind of a quick formula that has to do with directional cosines. Oh yeah, I should mention what directional cosines are. Remember what are directional cosines? That's the angle of something that's made with the major axis. Okay, so say if you have your vector here, okay, the directional cosines, the cosines of angles made with each major axis, something like that, all 3 angles, okay, and the angles values are the directional cosines, and it is in fact defined on page 63. We have already been through, I've shown you this before, but I just want to remind you this again in case you forgot what these are. This is the definition, and also how to calculate directional cosines. You just take the component and divide by its magnitude, which means yeah, anyways, that end up being the cosine of that specific angle. So once you have all 3 angles, then you know exactly which way the vector points. You don't know how big the vector, how long it is, but you do know which way it points, okay? And so that's why they're called that. And anyway, so next, let's look at theorem 7. We have a theorem back on page 40 that looks identical to it, okay? But only back then there was 2 dimensions, and now there are 3 dimensions. So because they're identical, their proof is also almost identical, which your book is going to skip right now, but we will be made to do it in homework. So I will talk about it in the homework. And so moving on, let's look at example C, okay, which is a practice of using theorem 7. So you take the f from example A on the opposite side of the page. You take the partial derivatives, you plug in some numbers, and you come up with what the directional derivative is at that certain point. So please do that yourself, okay? In this case, is the directional derivative end up being negative, so it's decreasing at some rate. in that direction. Okay. Now, so next, let's look at the meaning of the gradient, subsection 5.3. Now, from basic calculus, you might remember that the gradient is in the direction of the steepest descent, okay? As I put it this way, the direction maximum increase of f, grad f is, and then its length is, well, we'll call it L equals the magnitude of gradient of f. If you don't remember that, we are going to prove that fact right now, okay? And so let's look at the next page, page 82, where is so the length of the gradient is the magnitude of the maximum increase. Now the directional cosines are, by definition, the directional cosines of the gradient is of course by its direction cosines definition, is each item divided by its magnitude, which right now we call it L. Okay, L is the magnitude of the gradient of f. So then this is the directional cosine of the gradient f. And that's true because if you go back to page, I think, 63 and stare at the definition of the directional cosines again, okay, and you will quickly realize why this is the case. Because the directional cosines, as says, is just each component divided by the magnitude, which is exactly what it says here. So now that we know that, the next step we are going to talk about is if psi, okay, the direction that we're taking the directional derivative of is some direction, right? And then the psi somehow makes a specific angle, we'll call it theta, and psi makes an angle with theta. If that is the case, then if we look at the formula E in some pages ago on page 67, here's formula E. Look for E right on top. Now cosine theta of two, that is the angle between two vectors that makes an angle theta. Cosine theta is r dot s divided by their magnitude. So if you plug that formula in here, then we get this thing right here is that the cosine theta is equal to, okay, the directional, this thing is direction, so is given by cosine, what are these? Directional cosines, right? And then that will be equal to cosine theta times the magnitude, okay? Here's the dot product, and then of course the directional cosines, their magnitude is just 1. So then we end up with L cosine theta equals to this dot product, and which means that, and what is that? That this definition by theorem 37 on the previous page is exactly the partial, what do I have here? Yeah, is exactly this thing I'm trying to write down. Okay, that is, like it says, is the partial f partial psi a in theorem 7 on the previous page. That is this thing right here. Okay, the identical object. So that is partial f partial psi a. I should say partial psi a, okay, with an emphasis on z, but who gives a rip how we say these things, these Greek things, okay? And so, but anyway, so partial f partial psi a, it can also be calculated as L cosine theta if cosine theta is convenient for you to calculate. This will be used in one homework problem. I don't remember which one. We'll think about it a little later, but just bear in mind. So that's another way of calculating partial f partial psi a, and it's because of this situation. Now, so the next we are considering if since cosine theta is less than or equal to 1, right? So then the magnitude of this thing is at best L. So it's and therefore furthermore when the psi and the grad f are coinciding, that is theta equal to 0 or pi, either way, if they're parallel, then theta will be equal to 0, and therefore this will automatically be at maximum, right? Because at partial f partial psi is L cosine theta. So once cosine theta is 0 or pi, then the whole thing is maximized, and therefore Consequently, it is the maximum, that's the directional derivative. So when the directional derivative is maximum, and so when it equals to the gradient of f. Okay. So what that means is that the gradient of f, which is parallel to itself, is the maximum value, magnitude of any direction. All right, so next let's look at example D, which is just a quick example, which we have the function as defined in example C, where you can calculate the gradient and then calculate the L, which is the magnitude of the gradient, then calculate cosine theta, which is the angle between the gradient and that vector that's given, 2 minus 4, 2, and then calculate L cosine theta, which end up equal to partial f partial psi a. So please do that yourself, okay? Just a matter of plugging in some numbers. And then and in the meantime, I will move on to example E, which is slightly interesting. The book is talking about the rotation. Okay, let's say the rotation of a body, it has angular velocity w and is represented by some vector omega. Now this is a symbol here, okay? It looks like w, but it's not. It's the Greek letter omega, which is the small letter of the normal omega we normally think of, okay? And but anyway, this thing is pronounced omega, but it looks like w, but we'll call omega a vector. Now the vector omega has the magnitude of w, well, obviously, and then it is obvious because they look similar, so we'll choose the magnitude to be called w. So I guess it's obvious but not interesting. Anyway, since it's decided by the right-hand rule, that is, to calculate the angular vector, I mean this omega thing, what you do is your finger right hand wraps around which way it's turning. You know, let's say your finger points to the way it turns, and then your thumb will point to the direction of the vector. And so then if we have the origin, and then x is some point that's a distance h from it, then the instantaneous velocity of the point x is given by the vector v equals omega cross x. That's because the cross product is, that's because the v is perpendicular to omega and to x, okay? So v is the speed of this thing turning at x, okay? So it's turning that way. And then we can calculate the vector v as omega cross x. Now, and also the magnitude of v is equal to w times h. That is the area of the parallelogram that is determined by omega and x. Well, anyway, right. Let me see. Okay, so I want to quickly explain the physics part of this thing. It's not a big deal, okay, in the sense that we don't actually care, but I just want to explain why v equals to omega cross x. The big X means cross, so to not get confused. The reason is because in physics, the velocity, the angular velocity, is defined as wx sine theta, and you can see the triangle relationship of why that is the case. That is the velocity defined as the angular velocity times the distance away from it. So that is, which end up being, as you can see from the graph, is omega cross x. And yeah, that's all. But basically, all we care about in this point is v is omega cross x. Okay, so anyway, let's see, I should stand here so you can still see that. Okay, so let's move on. And then if in this case, then the magnitude of v is w times h due to something, yeah, you see, it says right here, and also because that's the result of the cross product. And then the area of the parallelogram, well, yeah, in this case, square, is determined by, of course, omega, the two vectors omega and x. So the speed x is the angular velocity, and then multiplied by radius h, okay? Yeah, see, the speed of x, angular, well, anything, by the radius h is w times h right? And then in the circle in which x is moving. All right, so that's just some physics part that we want to mention briefly. And like I said, if you don't understand the physics completely, we really don't care, okay? Just memorize the math part, which is v equals omega cross x, period. So omega cross x, if you were to calculate it out, well, if you were to write it out, let's say there's nothing to calculate, okay? We just have a bunch of, the cross product by definition equal to this stuff they show you right here. And then more interestingly, if you were to calculate the curl of omega cross x on a few pages ago, okay? Now, where was the curl definition? Right here. Let me move the page. Can you see it? Like this. Okay, definition 4, that's a curl definition, which is that thing. And if you stare at that definition and look at this thing right here where it says curl omega cross x, that's curl of the whole thing, okay? Omega and cross x, not just omega. So once you curl the whole thing and you look at the definition and stare at this thing for a few seconds, you can pause the video right now and stare at it and calculate what is omega cross x that is curl of omega cross x based on the definition right above. Then you'll be able to come out with that omega 1 plus omega 2 exactly in a few seconds. So please do that actually right now, okay? And then which end up being equal to 2 omega. That information, it will be useful in one homework problem, 11 or something, okay? And we'll talk about that after you do your homework. So your homework is problems, let me find my notebook here. Problems, let's see, 1, 2, 3, 4, 5, 6, 7, 8, and then 10, 11, 12, 13. All right, so please go do your homework. And after that, I want to talk about them. So problem 1, okay, and there isn't much to say about that. I think we are given a function and we're doing, well, same thing we did in basic calculus, just work out the mechanics of it all by taking partial derivatives and try not to mess up, which I did, as you see the scratches there. But once I found my mistakes and get things to come out, then things did work out or something. Anyway, so that is the grad of f, I guess. And the second derivatives, I had to calculate, what is that? The Laplacian or something. Anyway, so you plug everything in and things do work out to be the right answer if no mistakes are made. Okay, and problem 2, that's even shorter. You just write the divergence, follow the formula, and that means y1 is just x1. So it's like the identity function or something. And then you calculate divergence and then calculate the curl, and it all comes out nicely. Problem 3, similarly, apply theorem 7, and then partial f, partial psi is just, well, you copy down theorem 7. That's about it. And then problem 4, what are we doing in problem 4? Oh yeah, you plug in some numbers is similar to problem 3. So I did that, and if I didn't make a mistake on the numbers, then that should be correct answer. I hope I didn't make a mistake in it. But if I did, then the answer should still be pretty straightforward. Just ignore my mistake, okay? I couldn't confirm this, so because there's no answer in the back of the book, and I don't want to bother any harder than that. So next, let's look at problem 5. Now, problem 5 is we're now stuck with proving theorem 7, which the book doesn't want to bother. So to prove that is just a one-liner. It's almost identical to the proof that of the 2D version that we also studied in the previous chapter, okay? Except that now we have one more variable. So here is, so I scanned it into the computer to make the writing easier because there's a lot of writing. So first, let's review MVT. Now the MVT, the mean value theorem on page 46, I've extended here to a third variable. So on page 46, we only have a plus h, b plus k, which I scanned it here, okay? Except that I edited the file to add another c plus m in there, okay? And then minus f of a, b, and c. But other than that, everything works out the same. We didn't prove in, I didn't bother proving back in Taylor, when we were studying the Taylor series, that the Taylor series can extend to 3 dimensions. However, it was mentioned in the book, in the homework session. Let me show you quickly where it is. Yeah, this is a problem 13 on page, look at problem 13 on page 47. It says extend Taylor's theorem with remainder to functions of 3 variables. So it can be extended, which basically you repeat the proof of the Taylor's theorem, which at the time I was not interested in doing that. Okay, but right now I'm forced to write this thing out so that we can see it better. So well, basically it's the same thing as before. Before we only went from f1 and f2 with some theta in there, and you notice how theta is distributed. Theta is on each change, right? And so f of a plus h and b plus k, the old version with 2 variables, is equal to f1, okay, a plus theta h, b plus theta k, and then times h at the end. And that matters greatly. So whatever the change is, in this case h, will multiply by h, and the next partial derivative will multiply by k, but all things inside stay the same, you see. And then now we have a third variable, so we have the third partial derivative, and then times m, okay? But as you notice, everything in the parentheses stay the same. So we always have a plus theta h, b plus theta k, and then now we have c plus theta m. But otherwise, it's identical to what we used to have. So please bear this thing in mind, okay? There are a lot of variables, but nothing's different. So next, well, let's consider the definition of the directional derivative. This definition is, I didn't write down the page where I got this, but it's in this chapter, okay? And so just find this page 80. Whatever. So the definition of the directional derivative, which I copy and pasted here, equal to this thing, as you notice, is equal to f r1 and delta s cosine alpha 1. Okay, this is all copy and pasted from the book and etc. Now you notice at this point that let's compare this function to the MVT that we're going to apply. So in comparing, you notice a equals to r1, and then h equals to the entire delta s cosine alpha 1, which I also have it written here. See, so h is delta. To apply MVT, h will be we'll make h delta s cosine alpha 1, k is delta s cosine alpha 2, etc. See, and I also wrote it here in blue to remind you what we're doing. And the reason I write this stuff down is because there's going to be a lot of writing. And the proof itself is only a one-liner, but that is one long line, okay? And which is why the book skipped it, and we're stuck with doing it ourselves, and which is also why I scanned it into the computer so that I don't have to write so much. And anyway, so when we write it all out, what does that mean? To apply MVT, so let's focus on F1, okay? So it becomes F1A plus theta H, okay? So I wrote it down right here. And where, remember, what was h? H was delta s cosine alpha 1. And similarly for k and m. So this go all the way across. And don't forget that we're going to multiply by h at the end. And again, h is delta s cosine alpha 1, which I wrote down at the end of this row. See? And that's just F1. Okay, next, we will do the exact same thing to F2 and F3. Right here, see? So this is completely parallel to exactly what this is. And so please look at this and make sure everything makes sense to you. And what is h, and then k and m, and I'm applying MVT word for word, okay? And of course, theta has a condition between 0 and 1. So once you have worked through all that, that's the line. This is the one-line proof we're talking about. So we apply, and so once the MVT is applied, then you notice that there's a delta S down here and a delta S on the other end where H contains delta S. So all the delta S's cancel out. And then when we allow delta S approach 0, then all these theta, all the H, K, and M's vanished, right? And thetas, they all disappear, so we are left with this thing, okay? So therefore, the F3 all the way across is just partial F, partial X1, cosine alpha 1. Okay, that's the first one, and the other two are exactly the same, and that's how we proved this one-line did this one-line proof, except this one line took like 3 lines of a huge amount of writing, and if I was reading it by hand, you probably wouldn't be able to read it. I mean, even now, I think it's nicer to use the computer and use the color coding, okay? Then you can see H, K, and M very clearly, and it's also multiplied by H and Y, the delta S got canceled out, etc. But otherwise, this is identical, really, in principle, identical to the previous proof, which was also 1 line long. So, but anyway, I thought that was pretty nice to see this thing in 3 dimensions. But as you can see, the amount of writing expands by a lot, okay, by the time the 3rd dimension comes. And anyway, so that's problem 5. Next, let's look at problem 6. And problem 5 was a nice question where we did some bit of proof. Problem 6, we go back to cranking numbers. So please do that. Okay, here is problem 6, which I cranked the numbers, and we're supposed to calculate, what is that? Oh, yeah, partial f partial psi a with numbers given. So we plug it into the formula. First, the formula itself, and we got some answer right here. Okay, and then we're supposed to do it a different way. So I did. This is a different way on the previous page. Okay, where we calculate the L and then calculate cosine theta, which is kind of the same way, I think. Well, either way, the point is I ended up doing it this way. The cosine theta is the angle between the grad f and the psi. Okay, psi, that is an A, grad f and A. So anyway, that's the cosine theta, and then you come up with some numbers. And you notice that my 2 numbers, here's the one down here, and there's the one on the other side or up there. They are the same. So that means I probably got it right. So next, let's look at problem 7, which I need to find it. Here it is. Okay, problem 7, the same thing. We're doing some, some basic partial differentiation. And so the trick is to not mess up, and which I did. Unfortunately, I forgot the plus or minus or adding stuff up. But anyway, once I tracked down all my mistakes, then everything worked out okay. As you can see, then remember when you have these things added together, okay, that is x1 squared plus x2 squared plus x3 squared, it equals to r squared because of the definition. So then very soon you come up with del x del dot y equals to 3r minus r squared, because this r squared is the 3 things squared added together. And then the algebra came out to be 2 over r as the answer. Similarly, for the curl, when you do the curl, then you realize everything got taken out, and you only got 0. Okay, so that's problem 7. Problem 8, we are again doing some partial derivatives. It's a bit tedious to have to do this, but let's do it. Okay, so you do partial derivatives, and very soon that you realize that the it ended up being 0. Okay, and by the time all the math came out. So that is that. So next, problem 10. Okay, next, problem 10 is a matter of doing partial differentiation again. We'll calculate L. And L in this grad f, it just happens to end up being exactly 1. And therefore, L cosine theta, which is partial f partial psi a, is L being 1, and is just cosine theta, which equals to that. Okay, and this the fact that L cosine theta is equal to partial f partial psi a is listed on page 82. And so next, problem 11. Okay, I found it. Now problem 11, we're going to use this information that's on the same page but on top, where there's some omega business. Okay, we had omega curl omega cross x on the same page. So we'll let omega equals to a minus b. And therefore, and then in the meantime, notice that we have del cross y minus some constant. Being that del is the partial derivative operator, when it crosses y subtracting by some constant, is the same as crossing just y. Okay, so that should be exactly the same thing. So then we have. So we, in other words, curl of a plus a minus b will be the same as curl of omega cross, let's say, just x, okay? Because crossing a constant doesn't, del cross, the curl, well, anyway, we can just pretend that that thing is a constant. Well, just x, that is. So well, if it equals the curl of omega cross x, that would be equal to 2 omega, because that's what it says so at the top of this page that we verified earlier. And therefore, it equals to 2 omega, which is 2 of a minus b, and that should be the answer. So next, we have... Next, let's look at problem 12. What is the curl of grad of f? That equals to the null vector, and that was proved in basic calculus. So but we will do that again here, which is just a matter of writing stuff out, and you realize that these are all mixed partial derivatives. Okay, I mean f(3)2 is the same as f(2)3, etc. So everything got knocked itself out into 0. So that's problem 12. And problem 13 is no different. When you do divergence of curl, you realize that things all subtracted itself out into a big 0. And my 0 is too big here. I can't hardly read it. Like, what is that thing? But anyway, it means that it equals to 0. And that's problem 13. That should be the end of this section.